Welcome everyone to the session Designing Software with Effect Systems by Gautier DI FOLCO. Gautier is staff software engineer at Live Tools. We are glad that Gautier can join us today. Without further delay, over to you, Gautier.
Thank you for the introduction. Let me share my screen. Here it is. So today we'll talk about designing software with fixed systems. Just a bit of context. I learned at scale a bit more than 20 years ago. And it took me a long time before first teaching it and then shipping some code in production. And since 2023, I'm a founding member of the Haskell response team, which is responsible for all the vulnerability and security of the whole Haskell ecosystem. In mid-2024, I joined a company called Live Tours, which is focusing on creating guided tour in major European cities. So it's not a big company. We are roughly 70 permanent employees, um, while we were only seven 3 years ago. So we are in a hyper growth stage. And during my interview with my now boss, he told me that they had a 7 years old code base in his own, and at the same time that they wanted to migrate to a more structured approach with, for example, effect system, event sourcing, and so on. So before starting, um, I tried to learn Yesod and at the same time come up with a really simple API that I could refactor, and that's what will see today. But first, water effect. When Haskell started, they didn't have any kind of effect. I mean, see in an interview with Simon Peyton Jones that in the beginning they weren't even considering it because they say when you have strings, would you need to have any effect management? Joke aside, they had two approach in mind. At first, the first one was stream-based I/O, uh, which is mostly what you get with Interact. Roughly, you have a list of response, an infinite list of response in entry, and an infinity list of requests in output. And a more fine-grained approach, which is the continuation-based I/O, where you have a bit more context. Hopefully, not so long after, Phil Wadler came with I/O and Monad in general, because Monad is a really cornerstone in Haskell, because it's the only abstraction which allow you to sequentialize action or operation. The good part of I/O is that it's native. You don't have to reinvent the wheel yourself. It's quite ubiquitous in the language. And even if you take any libraries, if you take any libraries, you know that if they have a built-in monad, you have to deal with I/O, so it's already designed with that in mind. However, it's quite final, meaning that you can't get value from an IO without running the effect surrounding the IO. And it's quite opaque, meaning if you have a silo function, you don't know if it displays something on the std out, if it writes something on your file system, or if you do a post request over the internet. Quickly after, we came with transformers and ETL. there are two basic monads libraries coming with function operation. However, we have the n square problem definition problem. For example, if you have a first abstraction, which is a user repository, you have only one implementation, so only one instance definition. If you create a new one, you you have a new class, you have a new implementation, and then you have to replicate all the instance of the existing abstraction, and so on and so forth. For reference, just picture in my first code base, which was a middle size code base, I have more than 40 effects and nearly 100 interpreters, so it would have been impossible to work with. Not so long ago came the movement of what we call free monad effect system, where you have on one side um, dedicated monad which handles the composition, and on another side the standalone effect definition. For example, here you have the error effect with two operation or action which are throw and catch, and the monad which is called in Polysemy system, which is a short form of semantic, um, handles the composition, and you don't have to to deal with it. Let's see how it goes in practice. Let me share my code. Up. Sharing it. Okay. Okay. So I have a really simple API, which is the cart API. So just pictures going in on an e-commerce website. You can browse the website and just put some items or product in your cart or in your basket. So that's roughly what you get here. So I have a persistent implementation with product and cart, which is really simple. It only has an ID and a name, and in cart item, which has an ID, an associated cart, an associated product, and some quantity. There is few uh, endpoint, an endpoint to create a card, another to see the summary, and some endpoint to deal with the quantities. Also, the handlers are really straightforward because you for example here you get the body, you perform the persistent operation and you return it directly. I have few test cases in order to ensure that everything is working, but nothing too too fancy. Okay, so what is our point with introducing an effect system? Usually, you want to introduce one when you have hard-coded I/O. You want to be able to change dynamically. So, for example, here I will extract the I/O, so I will get some interface, and then I will be able to derive my effect from that. Let's take two endpoints. So, for example, the first one, which is dedicated to creating a new card. So, usually I duplicate the code, and the other one would be let's get a card item. Two simple ones. Then I rename my function. So here when we fetch card item. Okay, and the other one with me, quick card. The goal in the end is to do only simple refactoring, so we are sure that we don't break stuff needlessly. So they are not used, so my test should still work. Then we can simplify them only dealing with the end logic. So here, we can drop that. We need a text to create the card. Text. It will be new card name. Okay. So this one is not useful. Okay. New card name. Okay. Then I can substitute it in the code. Create the chart. Up. Okay. So this one should still work. And the other one is much simpler. Here we go. Yeah. Okay, so now I have extracted my IO. I can group this function and transform it into an effect. Here we are. Here we are. Okay. So an effect is actually in Polysemy at least a GTT, so general abstract data type, which is declared as the following. Let's call it cart E. Here I have suffix my effect, but in a real code base, I have dedicated modules, so I don't bother having a suffix name. So each effect has two type variables. The first one is a monad, which will be substituted by polysemy monad, and the other one is the return type. Then I borrow my function type signature. Here it is. I capitalize it. I change the return type. Cart in. And And then I call the make them, which will be creating my associated function, um, which are the which are the constructor without a capital letter, the first capital letter. Car- Then I have my type definition. I need an interpreter, a pending interpreter, in order to run the code we were previously running. In Polysemy, interpreters are simple functions which are actually you can find it in two forms. They are named run, the name of the effect, and the particularity of the effect. So here we have a persistent base effect. So I have a run cap persistent. Um, the first term you might see into the world is the legacy way to do it, which is you have the same, so the polynomial monad. Then we have an effect rows or effect stack, which start with the CART, which is the effect you are trying to interpret or consume. And then you have the rest of the effect row. And as a monad, there is a return value. And then you have the same thing, same R, so without the interpreted effect. Alternatively, you can find something I prefer, which is interpreter for. Interpreter for the name of the effect and the effect row. Okay. So here you have nothing, and finally you will have the effect implementation, the interpreter implementation. Here we have a function interpret which expects to have a case for every constructor. So case here, then we can reuse our previous function definition. Here it is. We can simply turn it into case statement instead of function statement. And then, as you see, my IDE is completing because we have RunDB, and RunDB are actually things which are specific to JSON. So hopefully, since we can't really instantiate RunDB on top of Polysemy, we can, however, embed any arbitrary model on Polysemy with a particular effect, which is embed. And we also have an issue with the general anomaly, which expects an IO. So we will add some requesting effect to continue, which says that R, so the effect rows should have these two effects, so embed of readers equal backend IO and embed IO. And instead of running DB, we will have embed. Okay. So if we run our code now, it won't work because as you see, create card and fetch card are not anymore handler for card API or handler something, but they are actually polysemy effect. So in order to go from any polysemy effect to a handler, we will have to come up with some function which will be run effect, um, run effect, which will go from a sense or polysemy un polysemy monad from API effect, which is an effector we will define to a handler for cart API of A. So at this point, there is two ways to proceed. Either we keep the cart API as it, and we simply call all the interpreters here, but that means that we will be locked in with this interpreter, or we change the cart API definition, and we will be able to directly inject the interpreter. So if I do that, cart API, f of get zone, okay, absent, and then okay. Now let's define what are our API effects. API effects are all the effects we will need in order to work with the with liaison. So it's not uncommon to do it at API definition level or in during the handler. However, you should, as much as possible, avoid to do it in the leave function because you want to have your leave function as using as few effects as possible to do it like that. We add card E. Then at this point we can say let's call it run effect. Yeah, run effect here. And then here we have to be able to create this function. So at this point, I create a new function which will be fn2, yes, which is API interpreter persistent, which will recode for the whole API. Which will take a connection bool because it runs on top of persistent, which run on top of a connection bool. Our same API effect and of A. Handler for carte API of it. Okay, so I am a pull here, and then we'll have to interpret things one by one. So usually I make some space uh, before. So I create that, I create a few, and then I try to interpret the stack. So as a reminder, I have this one. Here. So here I have a card key effect. I have to interpret. Hopefully there is only one interpreter. So I call it uh, run card card persistent. Okay. Then the next one, I still have only embed reader SQL backend. Actually, I usually when I have an embed, it's often quite often the last effect in the row, but here not the case. So we have to interpret it in terms of another embedded effect. So I have a run embedded, and then I have to run it. So it give me an IO, which is pip run equal pool of a pool. Okay. And finally, uh, I only have an embed IO, which is when I call the run m, which is, as you see here, taking the last embed of the on the effect code and turn it into a plain monad. And finally, since I'm in an IO and not in an owner, I have to lift it. So lift IO. Okay. Then I have to call it whenever I instantiate my API and say, okay, API in the persistent and in the test2. Oh, and we have an issue because we are trying to support run DB, which is a bit complicated. So let me skip that. Okay, so far so good. Let's just break uh, here for a moment. Here you see that the interpreter still have a get random IO, which is a pure IO function taking doing random stuff and taking some some character. Let's move. Uh, let's move a bit forward. And let's say I have introduced dedicated type, which is ID effect, which generates an ID, and it currently have only one interpreter. But let's say for a minute that we want a deterministic interpreter to be more precise, an incremental interpreter, which increments one by one the generated ID. So in order to do that, usually I take an existing working interpreter and I rename run incremental ID instead of a pure embed IO. I will use another effect which is an atomic state effect of an integer. Instead of taking this, I will show it in here. So I use the effect atomic state. Yes. Array, I increment it, and I return the current value. Okay. So let's say I want to use it in the test effect, for example. So I could naively say, okay, instead of run random ID, just use the incremental thing. Incremental ID. Okay. But it won't work because we don't have any atomic state in our stack. So again, naively, we could say, okay, just add something which is run atomic array. There is, as you see, there are many ways to deal with it. We need a URL because we had a database behind. So we could say, okay, just add it here and here. IRef of int. Okay. But it won't work anymore also because we don't have atomic state into our API effect. So a bad way to handle it would be to add atomic atomic state in here because doing so we will leak the underneath interpreter implementation. Hopefully, uh, Polysemy gives you many ways to reorder and to introduce new effect. Just to mention the right under, which allows to, for a given stack, add an effect under the current effect. So we have right under, which has given the head of the stack, just add an effect underneath. And it will nearly work because I have to add it a bit everywhere. There it is. And I have to create my new IRF here. Okay, just to make sure that I did something. It's not something that you really want to do in your production code, because if it will couple your test and with the environment, is to say, okay, let's assert that the ID is correct. Cart item key, which should be IC1. Okay. And just to show you that it works, if I do a mistake and I forgot to increment it, I have an error. Okay. So far, so good. Let's get back to my presentation. If I can. Okay. So the process is relatively simple in the sense that you have to locate and extract the IO part. Doing so, you will wrap one-to-one on one side, create the effect from the function type signature, and on another end, create the first interpreter with the function definition. Then you can come up with alternative interpreters and some other concept you I didn't have the time to show today. And you start over until every IO is well self-contained or fully when you don't have any more time. Okay, thanks for your attention, and if you have any question, I'm happy to answer it.
Thanks, Gautier, for such a wonderful session. I think people have catched up most of the things, so I can't see any chat or Q&As right now. So yeah,
Okay.
anyone has any queries, you can put it in the chat or in the Q&A section. So Gautier can answer your queries.
Yep. And anyway, I will be in the hangout room for after. So.
Yeah. So if you want to directly, Jens Peterson has said, thanks.
Thank you. Thanks, everyone.
Yeah, thank you, Gautier, for sharing your knowledge and experience with us today. Thank you so much for joining.